Hello everyone and welcome to another technical overview video of Black Square's Starship. Let's start by looking at the tablet interface, our window into all the systems in the aircraft. It can be dragged around the cabin and popped out of the screen so you can put it on a physical tablet you might have on your desk or perhaps somewhere in VR. On the options page, we can set persistent options that will be saved between sessions. This includes instant beta on touchdown, which is an option you might find useful if you're using hardware without a beta detent. You can also have the wheel chocks and covers deployed when you load the aircraft. Next up, we have the Payload page. Here we can adjust payloads and select exterior features on the aircraft like the gear downlock pins and the ground power unit. On this page, we can see that each wing has two fuel tanks. The forward main tank and its included hopper tank are located in the triangular root section of the wing. The aft tank is located underneath the engine nacelle towards the back of the wing. The aft tank will gravity feed forward when the aircraft is level, but not completely. There's a jet pump in the aft tank, which is a type of fuel pump with no moving parts that will pull fuel from the aft tank into the forward tank through the hopper tank whenever the engine's mechanical pump is sucking up fuel. In the cockpit, we have two displays with bar graphs and numbers that show us the total amount of fuel in each fuel system in pounds. When we push the aft quantity button, the bar graph is truncated to show us only the amount of fuel in the aft tank. Should one of those jet pumps fail or an engine shut down, fuel will no longer transfer completely from the aft tank to the forward tank, but there's no direct indication of this in the cockpit. This could lead to an engine shutdown while we're looking at the total amount of fuel in the system. If we see lots of fuel in the aft tank that's not being consumed, we should switch on the standby fuel pump to try to give motive flow to that jet pump and move the fuel forward. If that doesn't work, we'll be stuck with unusable fuel in the aft tank that moves our center of gravity rearwards as we continue to fly, meaning that we should select an airport for landing sooner rather than later. As usual, all the possible failures we've talked about so far are possible in a Black Square aircraft. Before we move on from the payload page, you can also see that the gross weight of the aircraft can be shown in yellow in addition to white and red. Yellow means that we're above the maximum landing weight for the aircraft, and we have to burn more fuel before we can safely touch down on its landing gear. Next up are the engine visualizers. These should look very familiar from other Black Square turbine aircraft, except these Pratt & Whitney PT6 engines have over twice the horsepower of the turbine Duke, with 1,200 horsepower each. At the top of the screen, we can see the fuel system we were just talking about, with the primary jet pump from the fuel tank, the electric standby pump, a fuel filter, and the mechanical engine-driven pump, all of which lead to the fuel control unit. As we power up the engines, we'll see fuel flow to the primary and secondary injectors, and oil circulate through these lines and change color with its temperature and viscosity. Every piece of equipment shown on this page can fail, and will indicate in red when it does so. Keep an eye on your inertial separator position and watch the amount and type of FOD you're sucking into the engines. For more details about Black Square's turbine engine simulation, I encourage you to check out the engine startup video for the turbine Duke. I've made even more improvements to my turbine engine simulation by working with PT6 operators, which makes Starship my best turboprop simulation by far. Next is the cabin visualizer. We'll have to come back to this one in the future because there's a lot more going on here than just the temperature and pressurization of the cabin. We can see there are 3 compartments here, and only the bottom one is what you feel sitting in the cabin. The middle compartment is what all those screens feel behind the instrument panel. and the forward compartment is what the equipment that drives those screens feels in the avionics bay, above the forward wing actuator in the nose of the aircraft. Keeping the avionics cool is essential to ensuring the longevity of the equipment in your Starship. It's largely a manual effort that requires some intuition, so that will be in another video. All the way to the right is the failures page, which works the same as in other black square aircraft, except this one has over 230 possible failures. This includes all the electrical systems, catastrophic engine failures, and everything in between, like propeller governors, clogged filters, and stuck bleed air valves. In a black square aircraft, almost everything can fail, so it keeps you on your toes and solving problems, just like in the real aircraft. By default, the failure system is in mean time between failure mode, meaning that each piece of equipment has a period of hours in which it's likely to fail. This approximation is good enough for NASA to estimate equipment failure on spacecraft. If you want an extra challenge, you can move the slider at the top of the page to increase the global failure rate. You can also select scheduled failure mode to specify time windows for individual failures to test your skills with specific scenarios. Finally, we have the live electrical schematic page. This should look familiar to King Air pilots because it uses the same triple-fed bus layout. When we turn on the battery master switch, it pulls down the battery bus tie and battery relay, connecting the battery power to the center bus and the triple-fed buses only. The triple-fed bus can be powered by the battery or either generator bus via diodes. Diodes only allow electrical current to flow in one direction, the direction of the arrow in the diode symbol. 3 buses can power the triple-fed bus, but not the other way around. The left and right generator buses are isolated from the center bus via the generator bus ties. These are normally open with only battery power, which leaves the majority of our heavy load equipment without power. This means that when we start up the aircraft, we have the minimum load on the battery that's required, and if there's an engine failure, we have automatic load shedding, meaning that we can extend the life of our battery until a safe landing. In order to power all of the equipment on the aircraft while sitting on the ground, we have to close the generator bus ties. This can be done by bringing a generator online, connecting the aircraft to external power, or moving the bus tie switch to the manually closed position. It will spring back to center, but the bus ties are now being held closed, powering all 5 electrical buses. We can hold them open again and isolate the buses at any time during the flight by moving the switch to the open position. To get a better feeling for the bus layout, we can monitor the voltages at each of these buses on the tablet interface or on the voltmeter in the cockpit. Underneath the voltmeter is a row of radio buttons that allow us to select each bus for display. We can see that the battery and the center bus have the same exact voltage because they're directly connected. But the triple-fed bus is around 0.8 volts below the center bus. Now that doesn't mean there's anything wrong, that's just because there's a voltage drop anytime we pass through a diode. Below the main bus layout, we have the avionics buses. Unfortunately, there isn't enough room on this page to show the hundreds of electrical circuits that are simulated in this aircraft, so instead we have just the avionics. They're spread out all over the buses in this aircraft to ensure some level of redundancy no matter what's being powered. There are also 2 standby batteries in this aircraft. One is for the last resort standby instruments in the center of the panel. This can be switched on at any time, and the white indicator lamp will illuminate when they're being powered by only the standby battery. There's also a standby battery for the ICAS, which is this screen here, and all of the avionics that drive it. This will give you engine instrumentation and, more importantly, the crew alerting system. When the main buses are powered, these batteries will be recharged. You can learn about all of the acronyms for these avionics like ICAS, SDU, ALI, and CHP in the manual that comes with your Black Square Starship. There's one page out of 200 dedicated just to learning the avionics acronyms. On this page, we can see also a few circuit breakers out of the hundreds that are located somewhere around the cockpit of this aircraft. These circuit breakers are all simulated, by which I don't just mean you can click on them. They're all slow blow thermal circuit breakers, which are activated by junction temperature. This means that when a system fails in this aircraft, it doesn't just pop the circuit breaker. It lies in wait for the next time that you use that system, and only then will the circuit breaker trip. You might not even notice a failure for several flights, since the failures are saved between sessions. You might be able to reset a circuit breaker, but it will probably heat up and trip again, so you'll have to troubleshoot. Speaking of troubleshooting, this aircraft has another method of diagnosing failures apart from the tablet interface. If we power up the rest of the avionics, we'll see on the multifunction display there's an avionics status screen. This shows us any fault codes from the LRUs, or line replaceable units, located throughout the aircraft and in the nose avionics bay. These might be telling us that the equipment has overheated, a circuit board has failed, or that a circuit breaker has tripped, and all we have to do is find it. I hope this gives you some idea of the complexity that's simulated inside this passion project. I truly believe it to be the most complex general aviation aircraft ever for Microsoft Flight Simulator, a title that I'm still hesitant to use, but I only hope to surpass with my future aircraft. In the meantime, I hope that you'll learn all of the remarkably unique systems that made Starship so far ahead of its time. Until then, I'll see you in the next video.